In the last class, we have obtained the expressions for the angular momentum operator and its components or the operators related to angular momentum operator in spherical polar coordinates. To be specific, we found that the x component, y component, and z component of the angular momentum operator takes this form when expressed in position basis using spherical polar coordinates, and the square operator has this expression. Our primary aim is to get simultaneous eigenvector and eigenfunction of L vector operator and its Lz operator, as these two quantities were introduced in the vector atom model. Note that in vector atom model it was introduced that the angular momentum has quantized values, and these values are LH cross. So, and for Lz it was MLH cross, where ML was allowed to have values from L minus L to plus L in steps of unity. So this was the prediction of quantum theory. When we switch over to quantum mechanics, we are to replace this this dynamical variable called by the corresponding Hermitian operator, and we must get the eigenvalues as the probable observed quantities. So the primary objective was to find out the simultaneous eigenfunction and simultaneous eigenfunction of L vector operator and that of Lz. But quantum mechanics doesn't allow us to find out the simultaneous eigenfunctions for L square and Lz, because they do not commute, as I have shown you in the last class. But it is found that L square operator commutes with each of its Cartesian components. So it is possible to have the simultaneous eigenfunctions of L square operator and any one of its Cartesian components, either x or y or z. It is possible to have the simultaneous eigenfunction of this operator. Keeping in this mind, we plan to find out the simultaneous eigenfunction of L square and of Lz. But this eigenfunction will not be an eigenfunction of Lx Ly, as Lx Ly, although it commutes with L square but not with of Lz. So why we are choosing Lz operator, not Lx Ly? The reason is firstly that Uhlenberg and Goldsmith, through their vector atom model, assume that the projection of angular momentum along the z direction, the direction of external magnetic field. In any coordinate system, z-axis is the straight axis of symmetry, except in Cartesian, where z-axis has no special status. It has equal status with Lx and Ly. Secondly, it is found that Lz is too simple if you compare to Lx and Ly. Lx and Ly depends on theta as well as on phi, while Lz depends on phi only. If you look at the spherical polar coordinate system, and if we rotate about the z-axis, then it is the phi angle which changes from phi to phi plus d phi. So this is the operator corresponding to rotation about z-axis. Furthermore, if we are interested in the simultaneous eigenfunctions of L square and Lz, the relation is obtained in terms of in closed form, and the simultaneous eigenfunctions of L square and Lx, although it exists in principle, but it is not very easy to get. So keeping all this in mind, we choose to find out L square and Lz's eigenfunction. So this is our objective. So our aim is to find the simultaneous eigenfunctions of L square and Lz. We assume this eigenfunction obviously will depend on theta phi. The eigenfunction is theta. If we assume the separation of variable technique, then it can be written as theta of theta, big theta of theta, and big phi of phi. So these are the wave function and their form in separation of variable technique. We assume that L square operating on the eigenfunction gives you lambda h line square theta. So this is the eigenvalue. Actually, lambda h square is the eigenvalue of L square operator. The H square, it is known that they see that the unit of angular momentum is h cross, so that of L square is h cross square. By choosing this, it is the dimensionless, lambda is the dimensionless eigenfunction. Dimensionless eigenvalue. And similarly, we choose the eigenvalue equation for Lz to be again the same one. H cross is the alpha h cross is the eigenvalue of Lz operator, where alpha is the dimensionless eigenfunction. So this is dimensionless eigenvalue of Lz operator. So our aim is to find out I first will start with this equation. So Lz operating on theta phi. This is Lz is minus IH cross del phi. Operating on this as per this trial solution. And on the right hand side, I will have alpha h cross. First thing, that this does not, del phi does not operate on the big theta, so we can cancel big theta on the either side, assuming the solution to be non-trivial, and we can also cancel h cross. And then this equation becomes here. Here I will have alpha on the right hand side minus IH cross phi, or this is so minus H cross. Solution of this is pi depends on alpha, some constant A alpha. This is the eigen. But in spherical polar coordinate, if we change phi go phi by phi plus 2y, nothing changes. Because we are landing upon the same situation. That is, this equation which leads to the fact that alpha is equal to n belongs to integer. That is to say, n can have values like this 0, plus minus 1, plus minus 2, and so on and so forth. This equation does not put any restriction on the maximum value of n that can be obtained. So the only say from phi equation we only get that n will have negative as well as positive integral values including 0, and there is no restriction. So our conclusion is that of this part phi of m of phi is equal to some constant a n to the power I m phi, which m is equal to 0, plus minus 1, plus minus 2, and so on. Now with this known value, we can now come to the eigenvalue equation of L square. So this is another facility that as we have chosen J like this, we have chosen L square and Lz pair. So the phi equation is decoupled from the J equation itself. Now I come to the this equation, this eigenvalue equation of L square operator. Now L square operator is minus h line square del 2 del theta 2 plus cot theta del rho theta plus 1 upon sine square theta del 2 del phi 2 operating on this, of which we have already known this part. So this operates on an to the power I n phi times theta of theta, and on the right hand side we will have lambda h line square a n to the power I n phi times theta of theta. So what we have done, we have used this equation L square, we have replaced the explicit expression of L square, and then for the wave function eigenfunction I have used this trial solution with phi n is this, as we have obtained from the solution of Lz eigenfunction. Here you see that only the phi dependent part is this, and when it operates on for non-trivial solution you can cancel phi on the side. So we lead to and then h line square cancels out. So we have minus the equation, the resulting equation has only theta dependence, so we write del 2 del theta 2 plus cot theta d theta. This brings in m square sine square theta upon theta. Let me explain the step once again. When del del phi operates on this part, brings you m minus m square times this, which we have written over here. This term has become minus m square and other things remain same. And for non-trivial solution, we can divide both the sides by this term because this is not zero. The resulting equation has only theta dependence. That's why I have changed the partial derivative by total derivative. This is the equation. Now, I will use a substitution. Let E is equal to cos theta. Then d theta becomes which in terms of u becomes, this is equal to sin theta minus sin theta, because u is this. In terms of u, this becomes 1 minus u squared to the power of u. Now the d2 theta d theta 2. This is d theta operating on d theta. So for we write this expression two negative signs, so we need not to bother about the sign. So it is 1 minus u square ddu operating on 1 minus u square to the power of operating on d. There are two terms. When this operates, we get 1 minus u square, because 2 half makes it power 1. And when this operates on this, this is the second operator, and there is another thing, cot theta d theta. For cot theta, I write it is cos theta by sin theta, so it is u upon 1 minus u square to the power of half. And for ddu, I write this expression. So altogether, these two power cancels, this becomes minus e ddu. So that's all. Now, if we write this equation together with all these substitutions, what I do? Minus. But if we take both of them on the same side, then this the sign is positive. So this is for this part. I write 1 minus u square minus this part coming from the first term, that is the double derivative term. Then from 14 dB we have this is from the first derivative term, and from there here we have first this term is there, so it is lambda minus l square, and for sin square theta I write 1 minus. So with the substitution u is equal to cos theta, the eigenvalue equation for L square takes this form. Uh, Let me write the summary and summary. The phi equation is n to the power I and phi, and this equation, theta equation, becomes d2 theta. These two makes it minus 2u minus 2u d theta du plus lambda minus m squared 1 minus u squared of theta is equal to 0. In our earlier class on Legendre differential equation, we found that the Legendre differential equation is 1 minus x squared. The Legendre differential equation, we call that Legendre differential equation is 1 minus x. Sorry, I missed this stuff. It was there. Y double prime minus twice x y prime plus alpha y is equal to 0. And since x is equal to plus minus 1 are removable singular point, we are interested in getting the solution between x is equal to plus, in between plus minus 1. This is the region of interest. This is the region of interest. If we put n is equal to 0 in this equation, we find that the two equations are same. So this equation with m is equal to 0 reduces to the Legendre differential equation, and this is known as associated Legendre differential. Associated Legendre differential equation. So here we have put u is equal to cos theta. The substitution is u is equal to cos theta. U is equal to plus 1 means theta is equal to 0, that is the positive z axis, and u is equal to minus 1 means the theta is equal to pi, that is the negative z axis. That is, if we are to include z axis, then the region of interest would be u between plus minus 1. Here we have a physical significance that u is equal to plus 1 is positive z axis and u is equal to negative minus 1 is the negative z axis. So we want a solution which is well kept all along the z axis, then we must consider the convergence of the solution. Before going to that, let me recall what we have done here. For any alpha, real alpha, the solution is converged, the infinite series solution. Solution of Legendre differential equation, LDE, we call it LDE, and I shall call it LDE. Is convergent in the open interval. Note that this open interval, but diverges diverge at x is equal to plus minus 1. if we set alpha is equal to a into L plus 1, but a belonging to integer and greater than 0, then one of the solution, the even solution for even L and the odd solution for odd L, one of the solution is a polynomial and hence is convergent in the closed interval. Note the change between this. I am going to write it. Note the change between these two intervals. It was in the open interval, but it is in the closed interval. That is to say, if we deal with any real alpha, say alpha is equal to 1.5, then the solution will be convergent everywhere except on the z-axis if you compare it. But if you want to have a solution which is convergent even on the z-axis, then any lambda value will not do. We are to take special value of this. The property of Legendre differential equation is also carried over to this associated Legendre differential equation. So we conclude for convergent solution on z-axis one must have lambda is equal to L into L plus 1 and the corresponding solution already, we know that already is an integer. The corresponding solution is known as associated Legendre polynomial. Here for alpha is equal to this, the convergent solution is known as PL, Legendre polynomial. Is a polynomial and known as Legendre polynomial PL of x. Here the corresponding solution is known as associated Legendre polynomial. So with this knowledge about the Legendre differential equation, I am coming back to this equation. For convergent solution in U less than 1 must have lambda is equal to L into L plus 1, where A is non-negative integer. Once the solution, once the polynomial solution of associated Legendre differential equation is known as associated Legendre polynomial. It is denoted as PLM of U. The property of that PLM legendary polynomial can be obtained from the legendary polynomial by differentiating it. Say we have m value is -3. We want to get, so p l, so m is equal to, say for example l is equal to 4. We want to get p l is equal to -3. Then we can get it from PL of 3, means here it is third derivative. This is the meaning of putting the absolute sign over here. So this is the relation. Now you know that it is PL is a polynomial of order L. It is a polynomial of order L. So we can at most differentiate it L times. Then we will end up with a constant. If we differentiate it for more than L times, you will get 0. The solution, it will give you a trivial solution. So for non-trivial solution, actually for non-trivial solution, in max is equal to L. Here we get a restriction, and another thing, and in mean is equal to minus. So we get a restriction that m can range from -L to +L instead of subunity, because m was an integer which was fixed from earlier, and L is an integer. So now we get an restriction on this is the as the ML quantum number that was introduced by Ulenberg and Goldsmith. So we have obtained the solution of the angular momentum problem. We see that the phi part was given by this, and the theta part is given by this. So the solution, the simultaneous eigenfunction, now coming to the simultaneous eigenfunction of L square and Lj operator. You remember that here the solution is this. So the simultaneous eigenfunction of L square and Lj is, it was originally taken to be theta phi. Now we know that two quantum numbers has initially we have written it as big theta of theta. Now we see that the theta depends on L and N, and phi depends on M. This is the simultaneous eigenfunction. If we write it explicitly, apart from some normalization constant, it is Plm of u, that is cos theta, times e to the power I n phi. The normalization constant is found to be 2L plus 1 upon 4 pi A minus mod n factorial A plus mod n factorial, factorial to the power half. This is the normalized wave function, and it has a special name YLM of theta phi. One may also write it as Y arm of r cap, because the r cap vector depends on the unit vector and r in present direction depends on theta phi. So instead of writing two arguments, one may also write it in terms of r cap. This is known as spherical harmonics. If you recall the solution of Laplace's equation, then we see that it is the solution of Laplace equation, is the solution of Laplace equation on the surface of a sphere. That's why the word spherical harmonics. If you recall that the Laplace's equation in polar coordinates are theta, if you solve the Laplace's equation in polar coordinates, then if you want to the solution on the circumference of a circle, then we get the circular harmonics. In that sense, spherical harmonic is the solution of Laplace equation on the surface of a sphere. So we see that there is a simultaneous eigenfunction of L square and Lz operator with whose eigenfunction is very well known, the spherical harmonics, and we call the eigenvalue equation. Eigenvalue equation was L square operating on this. Now we call it as YLM. Let me first starting point. Starting point was that L square operating on L square over L square. Now final solution is, conclusion is, L square operator operating on YLM of theta phi. The eigenfunction, simultaneous eigenfunction is theta phi, and lambda value is now changed to L into L plus 1 h line square YLM of theta phi. This is the eigenvalue equation, and it was Lz operating on theta phi was alpha h line square. This is now changed to restriction that L is equal to 0, 1, 2, etc. And for a given L, L is equal to minus L plus 1, minus 1, 0, 1. These are the values. A totality of 2L plus 1 values. So we see that the prediction of Gulenberg and Goldschmidt vector model has been reproduced through rigor of mathematical derivation. Only thing is that this expression, it was assumed that the eigenvalue of L is simply L, or L operator is simply L, but here we have to the eigenvalue of L square operator is any to L plus 1 instead of being L square. So there is an extra term Earlier we have found in the case of harmonic oscillator that as per Planck's law, harmonic oscillator energy was nh cross omega, but this is the quantum theory, the prediction of quantum theory. In quantum mechanics it was found to be n cross h cross omega in quantum mechanics, and we found that and we have shown that this appearance of 0 point energy of h cross omega by 2 is related to uncertainty principle. In the next class I shall show that this change from L square to L into L plus 1 is also related to the uncertainty principle. Only thing you know that when N increases, that is in the classical rhythm, the difference between L square and L into L plus 1 is very small. So the classical result is the same as obtained from both the theories, classical quantum theory or in quantum mechanics. Let me remind you once again, this is the prediction of quantum theory and this is the prediction of quantum mechanics. And today, in the next class, we shall have a detailed discussion on it.